Hello and welcome again to my physics video lecture series. Today's brief video is an introduction to statistics, part 2. We want to talk about confidence intervals and how to use them to compare the results of an experiment to our theory values. In order to understand this video, please note that it's not meant to be a comprehensive or exhaustive study of the subject. This is not being made as part of a statistics class, but rather as a part of an introductory physics course. So you can go take like a whole statistics course and get a lot more detail here. I'm kind of giving a very brief survey of all of this in a practical manner that can be used to do simple comparisons for labs and whatnot. Furthermore, if you haven't already watched the part 1 of this brief introduction to statistics, you should probably go do that first. Alright, so with those two caveats out of the way, let's get into today's video, which is about confidence intervals. So in order to begin this video, remember that our assumption in our experiments is that the errors in the experiments are very random, and therefore that the uncertainty in the experiment and the error in the experimental measurements is random. That means that we would expect for them to fall along a function described by the standard normal curve or the Gaussian distribution. So that has the form f of x is equal to sigma over root 2 pi times e to the minus 1/2 of x minus mean value of x over sigma quantity squared. Okay, and basically if you were to plot that function, you would get something that looks like this. Okay, so I've pulled this off of the website denoted down here. All right, and we are then assuming that the results of our experiment might be stated as x is equal to something like the mean plus or minus the standard deviation. And by the way, you could argue that this should be the standard deviation of the mean for the purposes of our comparisons. All right. Now, the beauty of this curve, what this function is telling us, is what's called a probability density. So f of x is a probability density. What that means is area from one x to another x, two values of x, in other words, on this x-axis. This is your f of x-axis. Area from this underneath that curve is probability of getting or of measuring the thing that you're trying to measure and getting a value between x1 and x2. So basically x1 less than x less than x2. All right. In other words, if I come down here and I find this area right here, then what I've found is the probability of getting between this and this as my measurement value for x. Now, with that said, these are in terms of what are called z-scores, and I'll get into that in a little bit. Essentially, this value right here is equivalent to x average, This is x average plus 1 standard deviation. This is plus 2 standard deviations, etc. This is minus a standard deviation. This is minus 2 standard deviations, and so on. And by the way, some sources, instead of using standard deviation, will use, instead of a sigma, will use a nu. I mention that because I have here from the ztable.net website a normal distribution which has gone and found these areas, although they've expressed them as percentages. Now you may be wondering, why would we express this as a percentage? Well, because it's a probability. By the way, if you find the area from minus infinity to infinity, then you'll get a value of 100%, or in other words, of 1. So if I want to know what's the probability of measuring between my mean and my standard deviation below, or my mean and my standard deviation above, I would basically go and I'd find those two areas, add them together, and find that it's a little over 68%. Okay. So the reason why I mention this as background is because what we're doing today is setting up what's called a confidence interval. Now these areas give you a probability of the next measurement being between those values given, but they also give you sort of like a confidence level. If you were to go and compare your result to some other number, and that number fell outside of this area, then we'd have a confidence interval of basically this much or maybe more, that the number is not the same as the number we're measuring. Note that if I happen to pick a number that falls in the range, like maybe the value happens to be right here, for example, that is not the same as saying that I have a 68% chance of this number being the same as the result. It just simply means we can no longer have 68% confidence that they're different. So the standard form of a confidence interval, or the standard statement, is something like this. We can be, and then parenthetically, up to, or at least, depending on how you've set everything up, some percentage confident that our result is not, and that means does not include and then basically the value we're comparing it to. And that's basically what the confidence interval says. So for example, let's say that our value here, our result, is 15 plus or minus 3. Okay, and basically we're claiming that 3 is standing in for our uncertainty, 1 standard deviation's worth. Okay, this would mean that let's compare to an expected value of, let's say, 11. So you'll notice that this range right here would run from 15 minus 3, so that's 12 less than x less than 15 plus 3, which is 18. So we can be, in this case we'd say at least 68.26. I'm basically just adding these two together, or in other words doubling this number, since these two numbers are the same. So we can be at least 68.2% or 26% confident that the measured result is not 11. Okay, and that 11 may be, for example, our theoretical result, in which case maybe our theory is off, or maybe we have some sort of systematic error present and not just random error. So how do we go about setting up a confidence interval? I'm just going to give you the steps here, or a set of steps. First step is sort of what that previous video that I referenced to, part 1, which is you must calculate or otherwise determine basically your result, your average, your standard deviation about the means. Okay, so go watch the previous video for how to do that. Second, use the result to determine a z-score. Okay, the calculation for that is usually like this. Z is equal to the difference between this and whatever you're comparing to. I'll just use value here, divided by sigma. So this is for value to compare result to. Okay. Step 3, look up z-score in population table or z-table. Okay, and then step 4, and I'll show you that table momentarily. Step 4, double the population and convert to percent. This is your confidence interval. All right. So now, what is this population table or z-table? Well, usually you just, there's a few things you could do. One is if you use calculus, you could actually calculate whatever z values you'd like using essentially this function and an integral. But for most purposes, including calculus-based, but for especially an algebra-based class or trig-based class, you'd go look up a table where they've done the math for you. And the way that you read this table is that you're looking at from z equals 0.00 to whatever value on the z table. You're looking essentially from there to there. And so like this right here would be the equivalent of z is equal to negative 1.00, and this right here would be z is 0. Okay, and so what percent falls between those two? So z equals 0 is sort of given as one boundary. 1.00, this is 1.0, this is 1.00, 1.01, 1.02, etc. So you're looking at this value right here for z equals 1.00. And this is 0.3413. Okay, and so if you double that, you get 0.6826, and if you convert it to a percentage, 34.13% times 2, which is your 68.26% that we talked about over here. So the way that you basically read this table is you've already calculated the z value you're looking for, and these rows are giving you the first 2 digits of that value up to 3.0. These columns are giving you the 3rd digit. So if I want 0.010, the 0.1 would be this row. The 0.10 specifically would be this column, and so I would get this number right here. If I wanted to get, say, 2.05, here's the 2.0 row, and then the 0.05 column is this column here, and so I look where those intersect. This would be my number. Okay, and so on. So that's how you basically go about reading this table. You just find your row and column where they line up, and then whatever number is shown there, that is your population score, and you have to double that and convert to a percentage to get your confidence interval. So let's do a very quick example. Okay, so here's our example. Let's say you're doing an experiment where you're trying to measure free fall acceleration, and you happen to do the experiment that the theory says that at the location where you are, it should be 9.80 meters per second squared. We'll learn both what this free fall acceleration is and how to calculate what it should be in future Physics 1 classes. Let's say that you do an experiment, and the result of your experiment, this is in terms of your average and your standard deviation of the mean, ends up being 9.72 meters per second squared plus or minus 0.04. So we want to know what's the level of confidence that these two differ from each other. Okay, so we've already got step 1. This right here is sort of like step 1 from this little recipe. So step 2, we need to use these and this to get a z value. So z should look like the difference between x and the theory value. I'm going to write theory instead of value here. Absolute value of all of that divided by sigma. All right, so that is the absolute value of 9.72 minus 9.80. This is, of course, in meters per second squared, all divided by 0.04 meters per second squared. And this difference is 0.08. That divided by 0.04 is 2. And so maybe we assume it's 2.00, but it certainly seems to be 2. Okay, so step 3, go look that up in the population table. So here is z equals 2.00. That would be this number right here, 0.4772. Okay, so we just found that P is 0.4772. Okay, so that means that the confidence interval is 2 times 0.4772 converted over to a percentage, and that ends up being 95 point, believe 0.44%. So we would basically conclude we are about 95.44% confident that there is a difference between theory and experiment. And you might argue that in fact we only had this first digit of 2, and so if you came over here and looked, we could distinguish between 2 and 2.1, but not between 2 and 2.00 realistically. And so probably looking at the values on here, we should just round this to maybe the first couple digits. So we have about this level of confidence, 95 to 96% confidence. Okay, last little thing before we close, which is coming back to this slide. This is assuming that what I want to do is compare the theory to the result of an experiment. I can also compare the results of 2 experiments. The recipe is fairly similar to what we had before. It's just that now what we have is a result for the first experiment. So we'll call that x plus or minus sigma x. And let's say the other one is y and sigma y. Okay. To get the z-score, z will now look like the difference between the 2 averages, and of course you take an absolute value, divided by the sum of the 2 means. Steps 3 and 4 are identical to the prior, so we can come back over here and in some sense just kind of copy what we've written down here for steps 3 and 4 of this procedure, and then just paste it over here, and it is in fact the same. Like once we've got the z values, the rest of the procedure is the same as before. Alright, so I'm not going to do any example on that at the moment because the video is kind of on the long side already, but I will conclude with that, and hopefully this kind of lengthy-ish, though at the same time very brief, primer on how to set up confidence intervals has helped you so that you are able to do so for your lab analyses. So thank you for watching, everybody, and see you in the next video.